We're going to look at some extra examples for section 5.5 and 5.6. We'll start in 5.5, and our first example will be to simplify the fifth root of 243 a to the 10th b to the 15th. Here we want to try to get the radicand, or the part that's underneath the radical, to be raised to the fifth power. So we'll start by looking at the 243. Now, if you didn't know whether or not 243 has a perfect fifth root, then you would actually need to use your calculator and take the fifth root of 243. In this particular case, we would find that it has a perfect fifth root, which is 3. If it did not, then we would have to use our other methods for simplifying a radical. We can look at the a to the 10th, and that would be a squared to the 5th, and the b to the 15th we would rewrite as b to the 3rd to the 5th. Now we have everything raised to the 5th power, and we can take the fifth root of the 5th power, which leaves us with 3a squared b to the 3rd. We don't need to have an absolute value here because we're taking the fifth root. Alright, the next one we're going to look at is simplifying the sixth root of t to the 6th. Here we do have to be cautious. We're taking an even root of an even exponent, and our result is odd, t to the first power. So in that particular case, we need to write that as an absolute value of t. We're going to look again at a fifth root. Here we have the 243 again, but we have x plus 2 in parentheses all raised to the 15th power. We can treat that x plus 2 as though it's just one single term and rewrite that 15th the same way that we did with the b to the 15th in example 1a. So here we've rewritten everything raised to the fifth power, and again we take the fifth root of a fifth power, and that gives us 3 times x plus 2 to the 3rd power. Now we're going to look at some examples from 5.6. Here we have the quotient rule, where we are allowed to separate the numerator and the denominator under the radical. So we have the square root of y to the 8th over the square root of x to the 7th. Now our goal again is to get our radical, or our nth root, to match the exponent underneath. So since we're taking the square root, we want to try to have everything raised to the 2nd power. On the top, that's quite easy. We can do y to the 4th squared. On the bottom, we have to do a little bit more. We have to remember that x to the 7th means x times itself 7 times. If we group 6 of those 7 x's together and have x to the 6th, we can rewrite that as x to the 3rd squared. And then we're left with 1x being multiplied at the end. Now we'll want to use the product property in the denominator to separate, and then we can simplify. That will give us x to the 4th on the top, or the numerator, and x to the 3rd in the denominator. The square root of x we can't simplify. So since we have a square root, or a radical, in the denominator, our next step needs to be to rationalize. We can't leave that radical in the denominator. So to rationalize the denominator, we'll multiply both the numerator and the denominator by that radical. And the result, we'll have y to the 4th square root of x in the numerator. In the denominator, square root of x times the square root of x gives us x, and x times x to the 3rd is x to the 4th. Our next example, we're going to have 5 times the cube root of 100a squared times the cube root of 10a. Since we have 2 cube roots, we can use the product property to put both of those radicands underneath the cube root. That allows us then to kind of regroup things. If I look carefully at that 100 and think about it as its factors 10 times 10, then I can see I'm going to have 10 times that third 10, or 10 cubed. I can do the same thing with the a squared. Separate it, a times a, and then I've got that third a, and that's a cubed. Now I can use the product property to separate those, and then take the cube root of both cubes, and then multiply. So we have 50a as a result. Here we're going to look at adding and subtracting radicals. We discussed in class that we can't add or subtract radicals if they're not like. It's as though you're adding an x and a y. We can't add those, we'd have to rewrite that as x plus y. But if I had x plus x, I could simplify that and write it as 2x, or combine those x's. So we're looking to get like radicals here. So to do that, we're going to simplify each radical, and we'll start by looking at the 45. We'll try to think of factors of 45 that are perfect squares. Well, 9 times 5 is 45, and 9 is a perfect square, 3 squared. We'll do that again with 80. It turns out that 16 times 5 is 80, so 4 squared times 5 would be under our radical. And then the 20, again, is 4 times 5, 4 being the perfect square, or 2 squared. Then we'll use the product rule to separate, and then we'll simplify the radicals that we can simplify. Square root of 3 squared is obviously 3, square root of 4 squared is 4, and the square root of 2 squared is 2. We'll replace those into our expression and then multiply. So in the first term, 3 times 3 will be 9 square root of 5. The second term would be 4 times the negative 5, or negative 20 square root of 5. And the last term would be 2 times 4, or 8 square root of 5. Then we can look and combine those. We can combine the 9, the negative 20, and the 8, and we get negative 3 square root of 5. All right, here we're going to look at multiplying where we have two binomials with radicals. We will do this like we have with any other set of binomials we're multiplying. We will FOIL, and then we will simplify as far as we can. Here we didn't have any like radicals, so we can't combine any further than this. Here we have an example of a binomial, 4 square root of 2 plus 7, and we're going to multiply that by what's called its conjugate, 4 square root of 2 minus 7. So you just switch the operation from either plus or minus in the second binomial. We'll FOIL the same way we did previously, and you'll notice that the two center terms will eliminate. This will always happen. So we can shortcut this process. If we're multiplying a binomial by its conjugate, we can take the first term, the 4 square root of 2, and square it, which will give us 16 square root of 2 squared. And we can take the last term, the 7, and square it, which gives us 49, and it will always be subtracted. The first squared minus the second squared. So 32 minus 49 gives us a negative 17. Now we can use this idea of the conjugate to help us to simplify an example like this, where in the denominator we have a binomial that includes a radical. We saw rationalizing denominators earlier, where we had a radical that was multiplied by something in the denominator. Here we have something that's being subtracted. We could also have something that's being added. In that particular case, we can't just multiply by the square root of 3. We have to multiply by the conjugate. And that came in ahead of where I wanted, but that's okay. So here we're going to multiply by 4 plus the square root of 3 over 4 plus the square root of 3, the conjugate of that denominator. We'll FOIL, and in the bottom, again, we don't have to go through the FOIL process. We can just take the 4 and square it, and the root 3 and square it, and we're going to subtract those two terms. Then we'll simplify any terms that we can, and here you'll notice that our two center terms in the numerator will be able to be collected because they are like radicals. So our result is 11 plus 6 square root of 3 all over 13. If you happen to have a denominator that divides into both terms, then you would want to simplify one more step, but we don't have that example here.